Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Compound B is 1,3,5-trimethylene, a cyclohexane ring bearing 3 exocyclic methylene, is equal to CH2 groups at the 1, 3, and 5 positions. Moving on to the next step. POCl3-pyridine is a dehydration reagent that converts tertiary or secondary alcohols to alkenes, elimination. So compound B is formed by dehydration of a triol intermediate. The triol intermediate must be a cyclohexane with 3C, CH3, or CHO groups that, upon elimination, give is equal to CH2 groups. Specifically, each exocyclic is equal to CH2 in B requires that the precursor alcohol had a C or H CH3 group. Wait, let us reconsider. Is equal to CH2 exocyclic means a CH2 double bond EXO to the ring. The carbon in the ring is sp2 and the exocyclic carbon is equal to CH2. So the alcohol precursor would be ring CH2O. No. Actually, POCl3-pyridine eliminates an O and an adjacent H to form a double bond. For an exocyclic is equal to CH2, the alcohol is ring C, or CH3, a tertiary alcohol where CH3MgBr added to a carbonyl on the ring. So if A has a carbonyl group directly on the ring, example, C is equal to O, or CH3MgBr adds to give ring C, or CH3R. Then POCl3 eliminates to give ring C, is equal to CH2, if R is equal to H, from aldehyde, or ring C, is equal to CH2, if it's a ketone where the methyl from Grignard becomes the EXO methylene after elimination of the ring H. Actually for a ketone C, is equal to O, in the ring, CH3MgBr adds to give a tertiary alcohol ring C, or CH3, then elimination, loss of H from adjacent ring carbon and O, gives endocyclic alkene, not exocyclic is equal to CH2. Moving on to the next step. For exocyclic is equal to CH2 formation, we need an ester or acid derivative. When an ester, CH3, reacts with excess CH3MgBr, two equivalents, the first equivalent adds to give a tetrahedral intermediate that collapses to a ketone, methanol leaves, then the second equivalent of CH3MgBr adds to give a tertiary alcohol, ring C, or CH3, 2. Then POCl3-pyridine eliminates to give ring C, is equal to CH2 as an exocyclic double bond. This is because from C, CH3, to O, elimination of H from 1 CH3 and O gives is equal to CH2, exocyclic. And for the final step, B has 3 exocyclic is equal to CH2 groups. So A must have 3 ester groups, CH3, on the cyclohexane ring at 1, 3, 5 positions. With large excess CH3MgBr, each ester reacts with 2 equiv CH3MgBr to give CH3, 2O at each position. POCl3-pyridine then dehydrates each tertiary alcohol to give is equal to CH2 exocyclic double bonds, yielding 1, 3, 5 tris, methylidene, cyclohexane is equal to compound B, compound D is 1, 3, 5 tris, methoxycarbonyl, cyclohexane, trimethyl cyclohexane 1, 3, 5 tricarboxylate, which has 3 methyl ester groups at C1, C3, C5. This perfectly matches the requirement. A. Trialdehyde, CH3MgBr adds once to each CHO to give secondary alcohol ring CH, of CH3 elimination gives endocyclic or vinyl alkene but not exocyclic is equal to CH2 with the correct substitution pattern for B, mixed ester aldehyde ketone would give mixed products. The ester portion could give is equal to CH2 but aldehyde gives secondary alcohol. Not giving is equal to CH2 upon elimination without correct substitution, and overall would not cleanly give the symmetric trisubstituted B, C, two ketones and one ester. Ketones with CH3MgBr give tertiary alcohols ring C, or CH3, with adjacent ring carbons. Elimination from these would give endocyclic double bonds, not exocyclic is equal to CH2. Only the ester group gives is equal to CH2. So this would not give 3 is equal to CH2 groups. D. 3 methyl esters, each ester plus to CH3MgBr, C, CH3, 2 of, then POCl3 is equal to CH2 exocyclic. All 3 positions give is equal to CH2, producing compound B. This is correct. Therefore, the correct answer is D. Therefore, the correct answer is option D.